Hey you, it's me. Let's talk about cyclic sort. Cyclic sort is a way of sorting an array in place in linear time. When we say we're sorting something in place, that means we are not creating a new array, but we are rearranging the original array. This algorithm is a special case for sorting, which is normally in log n time at best. For this case, every element in the array must be translatable to an index, which will represent its position. For example, say we have this unsorted array of 3, 1, 5, 4, and 2. We can use the value of the elements as indices. Or say we had an array of objects like ID 0, ID 4, ID 2. In this case, we can use the value of the ID as the position in the array. The problem statement for cyclic sort will normally give us a couple of crucial details. This will include the range of values in the array. A lot of the times we'll see this range as 0 to n or 1 to n, but it can be any positive offset from 0. We use that to help us sort the array by mapping the elements to their true index, which we calculate by taking the difference of the offset from the value. If we go back to our integer array example, the range for that would be from 1 to n. How we can utilize the offset to sort our array is by taking the element 3. Since we know we're at an offset of 1, we will take 3 minus 1, which is equal to 2. So 3's position should be at index 2. We can see 5. 5 minus 1 is 4. So 5's position in this array would be at index 4. Another important detail to know about cyclic sort problems is they almost always have another additional step, a find step. This is where you would be tasked to find the missing element or find duplicate elements. It is important to note what the second ask is, but we can almost always treat it like a second separate algorithm. First we do our sorting, then we take care of the second ask. You might be asking yourself now, wouldn't this take longer than O(n) to do? Well, actually, no. The combination of linear times is still linear. Sorting is O(n), searching is O(n). So when we have O(n) plus O(n), that equals O(2n), which we can drop the coefficient and just get O(n). Now that we know the bigger picture on how to find each element's true position, that leaves one challenge left: sorting the array in place. Because sorting in place means that we're not creating a new array to place all the elements at their correct position, we're going to use a swapping method to swap every element until it eventually is in its correct order. If we look at our unsorted array example, we can see that the first index is index 0, and the element at that spot is 3. Because the range of this array is from 1 to n, we know that eventually the element 1 will be in this 0th index position. We'll approach this by continuously swapping whatever is at index 0 until eventually we have the element 1 at index 0. Then we'll know we can move on to the next element to try swapping. Element 3's true position in this array would be at index 2. So let's swap it with whatever element is at index 2. In our case, it's going to be element 5. Now we have 5 in the 0th position. We're going to now swap 5 with whatever is at its true index, which would be index 4. And because we still don't have 1 in our 0th index position, we need to do another swap. This time, we're going to swap element 2 with its true position, which would be index 1. And look at that! Now we have 1 in our 0 index position. And our entire array is sorted just by making 3 swaps. In this example, we definitely lucked out by being able to sort the entire array just by swapping the elements at the 0 index. Since we could iterate multiple times over the same index, a for loop would be a little challenging here. A while loop, on the other hand, might be a better fit. The while loop will keep running, and we'll move on to the next step only when the element at our index is the appropriate element. We can put this all into practice now and try solving an actual problem. This one is on LeetCode. 448, find all disappeared numbers in an array. Given an array nums of n integers, where nums index I is in the range 1 to n, return an array of all the integers in the range 1 to n that do not appear in nums. And you can see here they give us 2 examples, but I want to point out this follow-up section down here at the bottom. They ask, could you do it without extra space and an O in runtime? The reason why this is a follow-up is because the more common solutions will solve this problem in O in log n time. That's because, as I said before, most sorting algorithms will run at best in that time range. We can break our problem statement up into 2 distinct asks. The first ask is to sort the unsorted array. The second ask would be to find all elements that are missing from the sorted array. So since we want to sort first, and we know we're going to use a while loop, let's create our iterator. We can also create our missing items array at the top. We'll use this in our second ask. While I is less than length of nums, we can create a helper variable that we'll use to hold the true index. This is what we use to compare our current element against. Because the range of this sorted array will be from 1 to n, we know our offset is by 1. So we'll create our variable true index that's equal to nums index I minus 1. If nums index I does not equal nums index true index, we will swap our element at index I and our element at true index. Now, Python has a really easy way of swapping. Nums index I, comma nums index j equals nums index j, comma nums index I, but it's also good to just know how to swap in other languages too. So here we have this swapping function. It takes in an array, your first index, and your second index. Inside of the function, we create a temporary variable. This is going to hold the element at array index I. Now we change the value of array index I. This will be equal to array index j. And finally, we change the value of array index j. This will be equal to temp, which was the original value of array index I. And this does the same thing as this Python one-liner does. Our else statement, this just basically means that nums index I did match nums index true index. So we can increment our iterator and move on to the next element to the right in the array, because it's already at its true index, so we don't need to do any swapping. When we get outside of this while loop, that means that we've sorted through the entire array. So now we need to go back into the sorted array and look for our missing element. This will be as easy as just checking if the element matches the index with an offset of 1. For x in range of length of nums, if nums index x does not equal x plus 1, we will add x plus 1 to our missing items array. After we've iterated through the entire sorted array, we can now return our missing items array. And that's it, we found all the missing items. So in this video, we went over the basics of cyclic sort, and we looked at a problem on LeetCode to get a sense for it. Cyclic sort can be a tricky problem. But the giveaway to see if it's an appropriate solution for a problem is if the problem statement asks you to sort an unsorted array in O in time. And remember, you can almost always split up your problem statement into 2 separate asks. Your sort and then your find or your search, whatever the second one may be. So thank you so much for watching. I hope this was helpful. Don't forget to like and subscribe, and leave me a comment if there's any problem on LeetCode that you want to see solved, or if there's any specific kind of pattern or algorithm you want to go over. I have so much fun making these videos, and I really hope that they're helpful for you. So from me to you, have a great day. Igorigums.